Okay, so this last week of class, we are learning about limits, and limits are a very big topic when you get to calculus. Limits sort of form the basis of what calculus is. And so you usually have to learn what it is and learn how to find limits before you start getting into calculus, because calculus was actually the definition of a derivative, which is one of the two biggest calculus concepts, is based off of it has what's called the limit definition of a derivative. So you need the limit to understand that. So limits sound scary. They're really not as bad as you may think. The hardest part is probably the theory behind them. So certain calculator. So I use the TI-30X2S. This is the one that it works for most of the engineering classes because it can do polar coordinates and degrees and all that kind of stuff. If you have the money for a graphing calculator, you could buy one, but they're like 200 bucks. So I have a TI-89 graphing calculator, which, let me pull this. I don't know how much it was when I bought it. I had to buy a second one because my first one got stolen. But it can do, I have the TI-89 titanium. It could do calculus stuff. The TI-83, yeah, the TI-89, yeah. So if you still have that, but that's expensive, and there are online graphing calculators, so I don't recommend buying that unless you absolutely have to, because it is expensive, and most of the time you can use websites. Desmos for graphing. Wolfram Alpha is what I do a lot of calculus in these days. It's a website where you can just type in kind of what you want to do. Actually, let me pull that up so you can see it. So, Wolfram Alpha. Okay, so Wolfram Alpha is pretty amazing, and it's based off of this whole programming language that is called Mathematica that I actually did all of my math in. I programmed in that. But you can do various things. So it has calculus and analysis, and it has examples. So if you want to do a derivative of something, it tells you just type in derivative of, and then you put in the function. So you can do calculus stuff in this. And so it even does limits. So I will click on this, and you just have to make sure you type it in correctly, and then it will compute the limit for you. And then if you pay for it, you can get step-by-step solutions. So you'd have to pay to get that. Otherwise, you at least get the answer so you can check your answer. So Wolfram Alpha is basically like a fancy graphing calculator on the web. They also have a phone app that I purchased. It has a little keyboard that you can type in Greek symbols and stuff like that. You can even graph things in here. So I can graph x squared and just type in graph. And then for the most part, it figures out what you're trying to do. And then you can see a graph. So you can use that instead of buying a TI-89. This is completely free for the basic stuff, and then you can see their student pricing for a whole bunch of other stuff if you want to do that. I don't know how much that is. $4 per month, that's pretty cheap. I wonder how much I'm getting, because I'm not paying the student price. I am paying for this. I'm not signed in to get it, but that's pretty good, $4 a month. And then if you could just cancel after you're done with calculus or something, that's pretty good. Semester, $5 if you do a semester. Okay. So yeah, Wolfram Alpha is probably my go-to, and it does so much other really neat things. Actually, I don't, way back, if you remember, actually, let's do this one instead, the Batman function. It does some pretty cool things. Oh, maybe it says Batman equation. Yeah, this is what I want. People have done pretty neat things. They figured out how to make Batman with an equation. So this is the whole equation to make that Batman symbol. So I like Wolfram Alpha because it does fun things. I mean, it's crazy when you think about, oh my goodness. But yeah, you can actually do really neat stuff with it, and people are crazy enough to do that. So yeah, this is actually a great way to check your limits for this week. So Um, that is a good question. So let me pull up. So let's take a look at limits and how they work, what they are, all that good stuff. So you have actually done stuff with limits before, you just didn't know it. In college algebra, we actually did two different problems that involved limits. So we looked at end behavior of a polynomial and asymptotes of a rational function. Whenever I teach college algebra, I usually point that out and say, hey, these things are going to come up. This is actually a limit. You'll learn about this in pre-calculus. So the limit of a function is basically you're saying what value does this function approach as we approach something else. So as I head towards x equals 6, where does my y go? That's essentially what a limit is. It's asking what happens to y as your x goes to certain things. So you're just investigating a function. So since we've seen this in terms of end behavior and asymptotes, that's where I'm going to start this off. So I'm going to start with limit in regards to end behavior. So I'm actually going to zoom in. So way back in college algebra, you learned about the leading coefficient test. So the leading coefficient test was basically telling you whether something went up or went down depending on what it looked like, and then depended on if it was an even or an odd function. And that was called the end behavior. And so the end behavior, when your degree of a polynomial is odd, it usually looks like a cubic of some sort where your left and right go in opposite directions. And if the leading coefficient was positive, it increased as you went to the right. If your leading coefficient was negative, it went down to the right. So that was the end behavior. And then if you had something that was even degree, like a quadratic or something to the fourth, they went in the same direction, either up for a positive leading coefficient or down for a negative leading coefficient. Now, what you may not have paid attention to is this actual language here, because it's kind of confusing. And then we have these symbols here. You see f of x, this arrow, that arrow means goes to. So f of x goes to infinity as x goes to infinity. This was basically the fancy way of indicating a limit. That we're saying as x gets larger, what happens to y? Well, y goes to infinity. Or if you're looking at the left side, as x gets smaller, what happens to y? Y gets smaller when you're looking at the odd. So these are actually limits, we just didn't call them that. Now, when we talk about limits, we have very specific notation. So I'm gonna have to flatten out my tablet so I can not kill my wrist here. Okay, so when we indicate a limit, we abbreviate it with lim. If it would let me draw. For some reason, that left corner, it just does not like. So we abbreviate limit by lim, and then underneath it, we put where x is going. So let's say as x goes to infinity. And then you put what the function is. So the limit as x goes to infinity of f of x equals, and then you say, where does that go? So if we are looking at this graph right here, as x gets larger, our y goes larger, and it goes on forever. So it goes towards infinity. So you would translate that end behavior this way. You would write the limit as x goes to infinity of f of x equals infinity. Let's say we take a look at this one, and we're also looking as x goes to positive infinity. So as x goes to positive infinity, our graph is going down, down, down. So the limit is negative infinity, because it's going down towards negative infinity as our x gets larger. So we're just saying what happens as x gets really big or really small, what happens to the y value. And then it could get to a single number, or it might go to infinity. And so we can say, oh, this equals infinity. Now, it never gets to infinity. It approaches infinity. So it doesn't, a limit doesn't mean it actually has to reach that value. It just has to go near there. And you can never touch infinity. So it's just going to head towards there forever. Now let's look at this in terms of asymptotes. So we used this notation a little bit with asymptotes as well. So when we're talking about vertical and horizontal asymptotes, so the line x equals a is a vertical asymptote of the graph of f when f of x goes to infinity or f of x goes to negative infinity. And then that's as x goes to a, from either the right or the left. So the limit as x went to some value a of our function either went to positive or negative infinity. So I'll just write plus or minus infinity because we don't know without an actual picture. But that's what we're saying as x went to some number. So if the vertical asymptote was at -5, as x got to -5, your y values either shot up towards infinity or they went down to negative infinity. That's the limit. And we also sort of talked about the limit as far as horizontal asymptotes, but that was sort of in the opposite direction, where you're saying, well, what happens to x as our y decreases? Now, limits are usually exclusive only to what happens to y as x does something. So we don't have a way to write limits for horizontal asymptotes, but we do have them for vertical asymptotes. So this will all make sense when we actually start finding limits. I just wanted to show you how you've seen things in the past and how we're going to be using notation for that going forward. So if you're trying to find the limit of something, there are basically three different ways. There is the numerical approach, where you create a table of values and then you see what number do those values approach. That one is hard if you are not looking at the right set of input values. If you are picking the wrong numbers to look at your table, you might get the wrong answer. So the numerical approach is not recommended, but you can do it. Then we have the graphical approach. I like the graphical approach. I like to use that even if I do the analytic approach because I'm a very visual person and doing it graphically helps me see what's going on. So with the graphical approach, you would draw a graph by hand or use technology and then see what happens to y as your x heads somewhere. And then your last method to find limits is the analytic approach, where you're using algebra or calculus to find the limit. We're going to be focusing mostly on the numerical and graphical approach. Once you get to calculus, that's where you will learn the analytic approach. We can do a little bit of the analytic approach, but it's usually a lot harder if you're just looking at the equation and there's all these little tricks that you have to do. So we're just going to focus on the first two. And then you'll learn more about the analytic approach as you go forward. And there's actually a whole class that I had when I was getting my degree called real analysis, where you basically were doing nothing but limits. It was like the theory behind calculus. It was crazy. Totally really hard class. I don't know how Newton and Leibniz figured out calculus on their own. It's insane. So, okay, I'm going to do two examples of the table method, and you have the table method on your homework. So this is definitely one of them. They give you the table, one of them they don't. So both of these I'm giving you the table, but I'm going to sort of explain how you can figure out what numbers to use in your table. So example 1, complete the table and use the result to estimate the limit. So we are finding the limit as x goes to 3 of this function, x minus 3 over x squared minus 9. So we're saying as x goes to 3, what happens here? So if your limit is at 3, then you want to look on the left side and the right side of 3. So you want numbers smaller than 3 and numbers larger than 3. And you want to look close to 3, really close, which is why I have 2.999 and 3.001. But you also want to go a little bit far away from there so that you can kind of see the pattern. So I generally recommend that you, in the middle, you have whatever your value is. So it says as x approaches 3 here, so put that in the middle. And then just kind of add decimal places as you move out to the left and the right so that you can kind of center yourself at that spot. So when you're using the table, you are literally plugging in these values into your function. So f of x as x minus 3 over x squared minus 9. So you were plugging in these values for x into that function. So the first one is f of 2.9. So I have 2.9 minus 3 over 2.9 squared minus 9. So you have to do a lot of computation when you're using the table method, which is one reason why I'm not a big fan of it, because it just takes a lot of time. So, and it's all a matter of making sure that you can enter it in your calculator correctly, because if you mess that up, well, then your whole answer is going to be messed up. So I'm going to first plug in 2.9. So that gives me 0.169492, and presumably it goes on forever. So let's just use 4 decimal places here. 0.1695 is how that rounds. So then you want to plug in 2.99. So luckily that's fairly easy. You just plug in a 9 extra on all of your spots. And so that's 0.166945. Okay, so round to 4 decimal places. That would be 0.1669. And so then you do it with 2.99. So I'm going to just fill these in. That's 0.1667 when I'm rounding that appropriately. And then I plug in 3, and you get undefined. And so there's no value at 3. And that's because we have a rational function here. If I factored the denominator, x squared minus 9 is x minus 3, x plus 3. Those are vertical asymptotes. So we have a vertical asymptote. We have 2 of them, actually. At x equals 3 and x equals negative 3. Those are where the function is undefined. So at 3, it's undefined. We don't actually have a function value. But we can still find the limit. We can still figure out where this function is heading, even if we don't actually know what it is at 3. That's sort of why limits are helpful, because they give you an idea of what the number would have been if it wasn't undefined. Okay, so now I got to finish my table, and I'm going to plug in 3.001, and that's 0.1666. Then 3.01, that's 0.1664. And then 3.1, that's 0.1639. So now I've filled in the table. And now we need to estimate the limit. So we're estimating what happens as we get near 3. So at 3 we're undefined. The limit is not undefined. There is a number we're approaching. And so you look at either side of the limit, and you're kind of looking at the pattern. So at 2.9, we had our highest value, and then it was slowly decreasing. So if we look at the left and right of 3, we had 0.1667 and 0.1666. So we can average those two values to figure out approximately what our limit is. So I'm going to add those together and divide by 2. And so I'm going to say that my limit, if I can get this to right, limit is about 0.16665. That's a guess based off of our table. We're estimating the limit. We don't know what it is exactly, but if 3 was not undefined, we know that whatever number would be there would have to be in between the on either side. So we just take the average to kind of guess at what that number would be. Now we can actually find out the exact value here I mentioned that we're not really going to do any analytic limits, but I'm going to just show you how we can figure out what that is. And I'm going to just do that in purple. So we have our limit as x goes to 3 of x minus 3 over x squared minus 9. And we could factor and that the denominator, so that was x minus 3 over x minus 3x plus 3. So this is a little preview of calculus stuff that you'll have to do. If you notice, the x minus 3's cancel. So this is equal to the limit as x goes to 3 of 1 over x plus 3. And then as long as 3, you just pretend that you can plug in 3. We now 3 is not in the domain because there's a vertical asymptote. But if we were to plug in 3, that would be 1 over 3 plus 3, which is 1/6. So, and if you find what 1/6 is on your calculator, that's 0.1666 for forever, basically repeating. So we know the exact limit is 1/6, but we approximated it as 0.16665 based off of averaging the values on either side of my two values. So, are there questions on this example? Okay. So here's example 2. We have another table. We're going to do the same thing. Here we have the limit as x goes to 0. So now 0 is where x is going, so 0 is the center of my table. And now on either side, on the left side I need to have negative numbers, on the right side I need to have positive numbers. And because I'm at 0, I can have the same number on each side, just positive and negative. And you can see that I started just like on the previous slide, I have 3 decimal places. And then I decrease the number of decimal places as I go away from there. So we're going to do the same thing as on the previous slide. So our function f of x is 3 times the absolute value of x divided by x squared. Now if I found f of 0, I'd be dividing by 0. So this is also going to be undefined because I can't divide by 0. So that's why we need to take, that's why we need to take the limit. So I'm going to start with negative 0.1 and plug that in. 3 times negative 0.1 over negative 0.1 squared. And then it's basically plugging and chugging. So now the hard thing with the absolute value. So I have my absolute value, and I could try to do it by hand. I try to use my calculator to do it for me, but most calculators don't have an absolute value button. So this is one where you'd actually, like, you know, you have to think about it. You have to do the first part and the second part separate. So absolute value of a negative is a positive. So I know I'm going to have a positive 0.1 on top, and then I'm going to divide by negative 0.1 squared. So that gives me 33. Okay, hold on. I just got a text from my neighbor that we left the garage door open. So I will be right back to let my partner know because he was the one that left it open. Be right back. Well, I just got it on my phone, or on my Fitbit, the phone I'm charging with now. I'm back. Sorry about that. Okay, so we're just plugging in numbers here. So now I need to plug in negative 0.01. Again, I take the absolute, oops, that 33 is not correct. I'm looking at my calculator and I see that I accidentally plugged in 0.11 instead of negative 0.1. Why is this not letting me erase? Tara, did you find that? Okay, you're like, why is my math not right? I'm like, wait a minute, and why it's not erasing? Okay. Yep, see, I can type in things wrong into the calculator. It really does not want to erase. Okay. I'm going to just scratch that out. Let me recalculate this. This is the hardest part about doing about the table, is if you type it in wrong in your calculator, it throws everything else off. Okay. Did you get 30? I want to make sure. Okay. 30. Okay. Yes. Good. Okay. Let's put that back. Oops. Wrong. Wrong button. Oh, you thought it was in your calculator. Oh, yeah. You're also trying to calculate. Yeah. Okay. So that's supposed to say 30. Now, next one. Let's make sure I do this right. So I got 300. Double check my math. Okay, and then I got 3,000. Okay, now if I put in the positive, I should be the same, because squaring a positive is, or squaring it, yeah, squaring the positive is the same as squaring a negative, and absolute value of a positive is the same as absolute value of a negative. So I'm actually going to get the same numbers here in the other direction. So I got 3,330. So if you had to make a guess at what the value would be at 0 if it were not undefined, the left side is 3,000, the right side is 3,000. So we can estimate the limit at 3,000. Now we can't do this algebraically like I did the other one, because there's nothing to cancel out, simplify like there was on the previous example. Now I'm going to pull up Wolfram Alpha on purpose this time, just to show you how you would possibly enter this in. So the one we just did, you would type in limit x, and then I can type in a dash, and then the side arrow, x dash side arrow 0, 3, and then the vertical bar is an absolute value, and then divide x squared. So I can type that in. It's a little bit messy, but you can do it. And let's see what Wolfram Alpha says. So it's telling us it's going on to infinity, and then it gives us a graph. We estimated, because we said, well, on either side I have 3,000, so maybe it's 3,000. But if you look at the graph, there's an asymptote. There is a vertical asymptote at 0, and you can see both sides go up to positive infinity. And I can also, I'll put this in Desmos as well. Three absolute value of x divided by x squared. So you can see as I zoom out, it definitely gets straighter and straighter, and it's going to infinity. So this is an example where you may get a different answer for the limit based off of whether you used a table or if you use a graph. And I prefer to use both in case the table, you picked values on the table where it didn't make it clear. You know, according to our values on the table here, our best guess was, oh, maybe it's at 3,000 because that's what I got on both sides. But if you actually look closer and you look at the graph, you can see it goes to infinity. So this is why I don't really like the table, because it depends on what numbers you pick and how that works. So I'm trying to explain that here. So we have a vertical asymptote. Yeah, my eraser doesn't want to work. I better make sure I make no mistakes. Vertical asymptote is where the denominator is equal to 0. So we have x squared equal to 0, or just x equals 0. So there's an asymptote, and as we look at the picture, it goes up there towards infinity. So we know that the real limit is positive infinity because that's where we have an asymptote, and both sides go up towards infinity. Does that make sense, or do you have any questions on how that works? The ones on the assignments are not tricky like this, by the way. So if you're asked to do it by the table, if you use the table and you do reasonable numbers, you should get something close to the limit. It won't be a weird one like this. But I just wanted to show you how, depending on your method, because it's just an estimate, and what you pick, you may not actually see the whole picture. Okay, so now I have a couple graphing examples here, where this time we're not going to do a table because it's tedious, and we're going to just the graph. And I put the graph here for us already so that we don't have to do the graph. So we want to estimate the limit of, as x goes to 0, of tangent x over tangent of 2x. And so we are looking as x goes to 0. So what just happened? Okay, I don't know. What I saw on my screen was suddenly like my two slides combined. PowerPoint does not like me today. So as x from the left, oh, it just goes, every time I hit the drawing button, that is, okay. As x goes from the left, are you seeing that, or is that, you see it too? Okay. I think, no, I'm like, am I crazy? I've never had PowerPoint do anything weird like this before. Okay. Maybe I will stop sharing and start resharing again. So I'm going to just try that again, and maybe then it will behave. Okay, at least I know I'm not crazy. Okay, so as x, yeah, go perfect. So as x goes to the left, our y value is heading to where I put that arrow. Now we have to make sure we're counting correctly. So this is 2 up here. 1, 2, 3. We have 4 boxes, so that is at 0.25 on the y. Nope, that's at 0.5. 2 divided by 4 is 0.5. And then if we're heading towards 0 from the right, because we have to look at both sides as we're going towards 0, we're heading to the same value. The y value is 0.5. So our limit here would be 0.5. That's where we're heading from both directions. We have it on the graph. That's what it looks like. So that one's pretty straightforward. You look at the graph and you're like, okay, yeah. And we can even like verify that by typing that into Wolfram Alpha. So let me bring up my Wolfram Alpha there. Limit as x goes to 0, that can stay the same. And then I have tangent of x divided by tangent 2x. And you can verify you've typed it in correctly by making sure that what the math it displays matches. So you can see that's 1/2. That's correct. Now notice on the plot it has this open circle. That's because there's actually a hole at 0.5, because if you plug in 0 for a tangent, you get 0. So the tangent of 2x is 0, and you plug in 0, that's 0, so you'd be dividing by 0. So it actually is a hole there, but if that hole wasn't there, if that point was filled in, if it was continuous, it would be at 1/2. So it's kind of like if you filled in that hole, what would be the value there? The value would be 1/2, even though the function itself doesn't exist there. That's one of the reasons why we look at limits, because it allows us to see what happens to a graph even if we have things that are undefined. It's sort of a way to get around the undefined part. So Desmos unfortunately doesn't show holes, so you couldn't see that on the Desmos graph. So I'll just draw that in. Now here, this is a different graph. This one actually has a hole shown on there. So we're given a piecewise function, and we're using the graph to estimate the limit. So the limit as x goes to 2 of f of x. So as we head to 2 from the left, maybe I'll use a different color here. As we're heading from 2 from the left, we're going down to that where the hole is at 2. And then from the right side, we are also heading towards that hole. So the y value at that spot is 2. So that means our limit is equal to 2. Even though at that point the y value is 0, where the graph approaches is at 2. So we could ignore the little dot there. We're not looking for what the exact value is at that point. We're looking at where's the graph heading, and the graph is heading towards 2, even though that's not the actual value. So in this case, it's kind of unintuitive because you're like, well, at 2 it's at 0, but it's not. That's not the limit. It's a different concept. Does that make sense with this example? I know this is a little tricky one here. I actually saw some people on the self-assessment this week get this one wrong, because there was a question on the self-assessment like this. It's a little hard to wrap your head. Yeah, that's why I paused there. It is a little weird. It's like ignore the actual function values, but just see what happens. And the notation, you'll get used to it. Really, you're looking at, okay, x goes to 2. So you're like, okay, what happens when my x is getting there? So you're just looking at the x, and you'll get used to it, I think, with enough examples. And of course, you're going to see a lot of this in calculus. I think there's going to be at least 1 week of limits in calculus in Calc 1. So you will get much more practice on this. But once you kind of figure out the notation, it's not so bad. And I've got, one more example here. This one's a rational function. And I'm not even giving you what the equation is because it doesn't really matter. We just want to look at the graph. So it says that x approaches 3. So if I had, so 3 is right here on the graph. So these are counting by ones. So that's x equals 3. And we actually have a vertical asymptote here. So as x if we're getting towards 3, our graph is going down towards negative infinity. If we're going from 3 on the right, it's going up to positive infinity. They're going in 2 different directions. If your limit, or if your graph is going in 2 different directions, if it doesn't match at that point, we say the limit does not exist. If you've ever seen Mean Girls, I actually thought about I actually did have that. I don't know what I did. I swear I had put that photo on the first slide. I must have accidentally deleted it. But it might have been on my introduction. I put the Mean Girl quote. Yeah, but they say the limit does not exist. And that's because it's contradicting. Intro video, yes. I'm like, I know I put that somewhere. So because you're going in 2 different directions and it's not the same answer, one's positive infinity, one's negative infinity, it's not going to one spot. So we write does not exist. It's not undefined. It does not exist, or that's abbreviated DNE. So in cases like that, where it's not the same on both sides, we talk about the limit in terms of the left side and the right side. And we do that by putting little symbols as an exponent. If I put a negative up there, that means from the left. So that's from the left side. The left side is towards the negatives. So The left side, if you're going towards 3 and you're from the negatives, you're going down to negative infinity. And then if I take the limit and I'm going towards 3, and then if I write a plus, that's the right side heading from the positive numbers. That, as you're heading from the positives, that heads up to positive infinity. So that's the right side. So sometimes you will see positive and negatives in the notation to indicate whether you're looking at the left side or the right side of that x value. The negative means the left side, the positive means the right side. If the left and the right side match, we have a limit. If the left and the right side don't match, it does not exist. Does that make sense, or at least make a little bit of sense, even if it's not completely making sense? Okay, perfect. Now, don't worry too much. You're going to see this again in calculus. So you're not expected to master it. We're just giving you the most basic stuff. And actually, the assignment for this week, the application assignment, is less application. It's basically just doing limits. There's not really any applications in it. So usually people do really well with it because it's more the straightforward limits. And if you graph stuff, it makes it much easier. So most people do really well on the assignment for this week. So that was all the examples that I had set up to kind of give you a taste of the limits. Do you have any questions? Or even if you have questions on stuff that's not limit related, but just about the end of the course, I'd be happy to answer as well. You'll have a bunch. Okay, well, when you think of them, feel free to give me a call or email me. Tomorrow I'm at a conference until 3:30. So I'll be checking my email at the conference. I won't necessarily, it depends on if I'll be in an interesting session or not. If it's a boring session, I'll probably be replying to emails or grading. But if it's an interesting session, then, I may not respond right away, but I do get email on my phone till 5 o'clock. So at least between 3:30 and 5, I can check my emails. And then I'm at the conference again on Saturday. So anything that I don't respond to, I will definitely respond to by my office hours on Sunday. I'm actually giving a talk at this conference on live sessions. The name of this conference is really long. It's the Kansas City Mathematics Teaching Technology Expo. So it's all about showcasing the technology used to teach math. And so I'm like, well, I'm teaching math on the internet and I'm doing it with these videos. So I was like, I can give a talk on this. So that's what I'm going to be doing tomorrow. I'm actually the first talk of the day, so that's going to be fun. I have to finish writing it. I haven't done that yet. So I'm like halfway done. I really need to get that done. But I will be checking my email and everything while I'm there. And if I find any cool tools, I'll probably be testing it out in my next classes. So unfortunately, I just got my classes. I'm not teaching calculus next term, so you guys will not have me in your calculus class. But you might have me for Calc 2. So I usually teach Calc 2, so we'll see. But all right, so if you have questions, feel free to email me. I'm going to pop off so I can finish my talk. And hopefully you'll have a great rest of your evening and enjoy your weekend, or enjoy your Friday for sure. And yeah, if I'm a little late on grading discussions, it's because I didn't have time to finish it tomorrow. But thanks. I figure if I'm the first one of the day, then I set the tone. So if I mess up, everybody's like, I have no one to compare myself to. It's like, oh, not so bad. Exactly. Get it over with. So that's how I roll. I'd rather be in the beginning than at the end, because at the end, then people have expectations. So all right. Well, I'm going to pop off. So I will definitely be talking to you in the discussions. So